Hi students, welcome to my lectures on chemical reaction engineering. In this lecture, we are going to solve one problem of the adiabatic reactor. In the previous class, we have discussed about the derivation. In the today's class, in this particular lecture, we are going to solve very small problem. Given the temperature of the reactor, it could be batch reactor or CST or PFR or any reactor, what is the conversion? If you know the temperature, that means you know the conversion. That is what the beauty of the adiabatic reactor. Let a small recap. So, any reactor, it could be batch, it could be CST or it could be PFR. If it is insulated reactor, that means adiabatic reactor. No heat can come in, no heat can go out. No work you can do on the reactor, no work you can extract from the reactor. That is what the adiabatic reactor. That means given the conditions, what is the conversion? If you know the temperature inside this reactor, given initial temperature is T0, final temperature is T. Before the reaction, the batch reactor temperature is T0 and final the batch reactor temperature T. For case of PFR, the initial temperature is T0, the final temperature T. Then what is the conversion in these reactors if it is operated in a adiabatic mode? That is what the problem is. And the conversion from the energy balance, EB means conversion from the energy balance, XEB, sigma I equal to 1 to n phi I Cpi T minus T0 divided by minus of enthalpy of the reaction at standard state plus del Cp into T minus Tr. Tr is the enthalpy calculations if it is a reference state is given. Okay. T0 is the initial temperature of the reactor. T is the final temperature of the reactor after the reaction. So, using this equation, given the temperatures and all the data, let us find out the conversion we can expect. The problem is, example, in all these reactors, this reaction is happening. 1 mole of nitrogen plus 3 moles of hydrogen gives rise to 2 moles of ammonia. Then if you see this reaction in terms of nomenclature, A plus BB gives rise to CC. A, small b, small c are the stoichiometric coefficients. A equal to 1, B equal to 3, C equal to 2. If it is a batch reactor, the initial moles of A is 1 mole, initial moles of B is 3 moles in the reactor. If it is a CST or PFR, it is a continuous system. Then molar flow rate of A is 1 mole per second, that means every second 1 mole of A is going into the reactor. FB0 is the moles of B that is going into the reactor, that is 3 moles per second. Given these conditions, what is the conversion at a temperature 150 degrees centigrade? Let us find out the conversion using this adiabatic equation. We know if you expand this sigma, how many components are there? A, B and C, because in this reaction we have A, B and C. If you expand, sigma I equal to 1 to n phi I Cpi into T minus T0 is nothing but phi A Cpa plus phi B Cpb plus phi C Cpc. Because there is no inert, so you do not need to worry about phi I Cpi. If inert is there along with the reactions, you have to count the inerts here into T minus T0 divided by standard enthalpy of reaction at standard temperature plus del Cp into T minus Tr. T0 is my initial temperature of the reactor. T is the final temperature of the reactor. Tr is the reference state for every molecule. Given Cpa, mean heat capacities of A, B and C is given, okay, because we need Cpa, Cpb, Cpc, because mean heat capacities people take because Cp is depends on temperature. Here mean heat capacities we have taken. Let us assume that between this 150 degrees centigrade, within this one, Cp is not changing with respect to temperature. Let us take Cp value as a constant. Cpa, Cpb, Cpc is given. In the problem, the enthalpy of all the reactants and products is given at 25 degrees centigrade. If you refer to any book, handbook of chemistry or physics, any book you can take, an enthalpy of every molecule is given. Enthalpy of nitrogen, enthalpy of hydrogen, enthalpy of ammonia, everything is given. So, at 25 degrees centigrade the data is given. That means your standard temperature is 25 degrees centigrade, which is same that of a reactor initial temperature. That means all the reactants are going into the reactor at the same temperature. That means Tr is equal to T0. That means reference state is same as the reactor initial state. So let us take enthalpy of C. C means ammonia. Ammonia is minus 11,020 calorie per mole. Enthalpy of B means hydrogen. Enthalpy of A is nitrogen. Because they are at a gaseous state at their standard state. Enthalpy of B, that means enthalpy of hydrogen and enthalpy of nitrogen are 0. Only we have is the enthalpy of the ammonia. So as we know, enthalpy of reaction at standard state is nothing but enthalpy of the products minus enthalpy of the reactants. 2 times the enthalpy of C minus 3 times the enthalpy of B minus enthalpy of A, because that is what the stoichiometry is. So if you do that, enthalpy of the reaction at a standard state is nothing but minus 22,040 calorie per mole of nitrogen. Remember, when you talk about the enthalpy of reaction, you should talk in terms of molecule A. Why molecule A? Because we are comparing everything in terms of A. That is my limiting reactant. In our case, nitrogen is my limiting reactant. Now you have to calculate everything enthalpy of reaction in terms of A. Okay, that is why enthalpy of reaction is 22,000 calorie per mole of nitrogen reacted. That means per every mole of nitrogen reacted, how much of energy is getting produced. It is minus. That means during this reaction, energy will come out of the reactor. So come out of the reactor means heat production takes place. That is why it's an exothermic reaction. Okay. Let us take what is phi A. Fa0 by Fa0 for the CSTR and PFR. For the batch reactor, it is Na0 by Na0. Fa0, Na0 values are given. So accordingly, phi A is equal to 1, phi B is equal to 3, phi C, phi D are 0 because before start of the reaction there is no C molecule, and of course there is no D as such. Okay, C molecule, that means before start of the reaction there is no ammonia. If there is no ammonia before the start of the reaction, phi C equal to 0. Okay, let us do that. What is delta Cp? Because we need to evaluate each and every term. Now I know phi A, phi B and phi C. All the phi A, phi B, phi C values are here. Next we need is del Cp. We have already got what is delta H of reaction at a standard state. What is del Cp? 2 times Cpc minus 3 times Cpb minus Cpa. Cpa, Cpb, Cpc values are given. Specific heat capacities of A, B, C is given. So delta Cp is minus 10.12 calorie per mole of nitrogen per Kelvin. Okay. When you talk about the delta, okay, when you talk about the individual Cpa, Cpb, Cpc, that means you are talking about that particular molecule. When you talk about delta Cp, delta H, then you have to talk in terms of per mole of nitrogen, which is A, getting reacted. Okay. That is why delta Cp means minus 10.12 calorie per mole of nitrogen per Kelvin. Finally, you know all the values. Simply substitute in this equation, you get energy balance, that is conversion from these reactors. If that because additionally you should know the temperature, right? What is the temperature that is given at 150 degrees centigrade? That means the reactor is at presently 150 degrees centigrade. That means T is 150. My reference state of all the values is given at 25 degrees centigrade, and all the reactants are entering at a initial temperature T0, which is again 25 degrees centigrade. Given T, Tr, T0, all the values substitute in this equation, finally you get the conversion 0.149, nothing but 15% conversion around. That means if the temperature is 150 in this reactor, given the values, maximum conversion you can expect at temperature is 150 is 15% from this adiabatic reactors. So this is what a simple problem of how to use this equation and how to expand the terms. Okay, I hope you have learned. Okay, let us meet with some other day, some other lecture. Thank you.